get started. We got Hooke's law. I found out what he was. He's English, not Scottish, but never mind. Essentially, this is just some notes. I'm going to leave them here, but you can probably go back and watch the video and copy this down, whatever you feel you need to. Essentially, what he discovered was that if you take a spring and leave it alone, it has a natural length to it. And he found that if you stretch it a certain number of units beyond its natural length, and we'll call that distance x, that the force required to pull it from here to here, this distance x, is k times x. And k is a constant, it's a fixed number, and it depends on the spring, right? If you make the spring out of, slinky wire, it's a very small k value. If you make the, 1/2-inch stainless steel spring, you probably find that the k is in the hundreds. Now, when you're doing these types of questions, units are very important. Most of the questions, you have to make sure that you're doing them in meters and feet. So if it talks about 52 centimeters, remember that means 0.52 meters. Or if it talks about 7 inches, that's 7/12. And we're going to be doing quite a lot of decimals. So I'm not even going to make any attempt to make these answers pretty. We're just going to do them in the calculator and get 11.123, whatever it might be, and then round them off. So the force, right, to stretch the spring a distance of x is k times x. And if you want to do the work done in moving it from here to here, then it's the integral from x equals a, that's a inches or feet, whatever it is, a feet beyond its natural length to b feet. And it's basically just an integral from a to b. And very often, but not always, this number a is 0. And basically, you just integrate this. So the integration's not going to be hard, isn't the integration just going to be a power rule? It'll be 7x or 0.1x, but it's just going to be add 1 to the power, and off we go. So to finish off this section, and that's basically the first half done. And after that, we'll start on the last part, which I like more, because it's got nice and puzzles in it. And it's about pulling things up cliffs. But let's get this guy on the road. This is very similar to question 5 and 6 in the homework. So in this case, I've got a force of 12 pounds is required to stretch a spring 2 inches beyond its natural length. Now that information in blue is the information you use to find k. Now once you know what k is, right, it's a fixed number. Once you know it, it's the same number for always. You can then answer the question, which is in red this time, how much work is done in stretching it to 7 inches beyond its natural length? So that's going to be our first question. So I'm going to start off with Hooke's law that says the force to stretch it to position x is k times x. And we're told that it was 12 pounds, so the force is 12, and it's 2 inches. This is going to be k, but it's not going to be k times 2. What number will I be using, or what fraction, to be more accurate, will I be using? What will the 2 inches be turned into?
Would it be 2/12 or 1/6?
Correct. Remember what I said, always in meters, always in feet. Even if the numbers are in inches, you have to convert them. So we're happy just leaving that as 2/12, or you can turn it into a 6 if you want, right? Okay, so that means that we've got that, agreed? Sometimes this fraction just won't turn out well, in which case just turn it into a decimal and call it good, right? Turn it to nothing 0.123 if it ends up being like that. Now, what do you need to do now to find k? Got this? What do we need to do to get k?
Divide by 1/6.
Right. typically, I think it's a good idea to think of it that way because it's not always going to be a nice number. Sometimes it's going to be 0.123. So thinking about dividing this helps. Can you trust me that the answer ends up being 72? But that's something you can do in your calculator. So that gave me this. It now means I know the force function. Once you know that guy, whoops, let's try that again. There we go. Now I know the force function, right? That guy is going to be able to answer any question you want from now on. So for instance, in the red, the question that you are being asked is, how much work is done in stretching it 7 inches beyond its natural length? Now the formula for getting the work done is this one. So it's the integral from A to B of the force function, dx. In this case, it's going to be the integral from 0 and 7 inches. Can I call that guy 7/12? You happy boy? That 7 inches is 7/12. Rather awkward guy. And 72x dx. Right. Power rule 36x squared. Evaluated at x equals 0 and x equals. At some point, I'm going to have to bite the bullet here and turn these things into decimals. And then it's just going to be 36 times this guy squared, take away essentially nothing. And again, calculators are your go-to guy. 36 times 0.583 squared. And the answer to 2 decimal places is 12.24. In this case, the units are foot-pounds. Are you comfortable about the second part then? The first part is how to use this information here in blue to find the missing K value. And then the second part is the real question, because that's the only thing you actually are being asked to do. But you need to get this before you can do that. And this is how much work is done. Now, couldn't you change that to all sorts of questions? For instance, couldn't I say how much work is done in stretching it from 1 foot to 4 foot? Yeah, big stretch. If I had, wouldn't this integral be from 1 to 4? And if I said, you know, how far to stretch it 10 inches, wouldn't it be 0 to 10/12, and so on and so forth? And that's basically how you're going to do 5 and 6. Anything that you're not sure about? Are we good? Okay. Now, next one. Realize I wrote on that guy. It's essentially the same question. The only major difference is, have you noticed that I'm using metric? So it's newtons and centimeters, right? So here goes. A force of 10 newtons is required to stretch a spring 15 centimeters beyond its natural length. And then it goes on and asks us to find the work done. So the force function, according to Hooke's law, is that the force is 10 newtons and K times 15 centimeters is 0.15 meters. Hopefully you've done enough chemistry and physics, whatever, that you know how to turn centimeters into meters. Don't you just divide by 100? So 15 centimeters is that. Now, if you want to find K, I think in this case, it's much clearer, you know, that you're dividing, right? And I'm going to have to round this thing off because typically you get ugly answers because that's what real life is like. And it's about 66.67 to 2 decimal places. Now, once you know K, you've got your force function. And your force function is 66.67 K. Now, when it asks how much work is done in stretching it 45 centimeters beyond its natural length, the work done is the integral from A to B of your force function. In this case, it's going to be 66.6, no, I think that's next, 67x, and 0 to 0.45. Are you happy with the 0.45 thing? Right, 45 centimeters, 0.45 of a meter. Right, from 0 to 0.45 in this case. Right, I'm putting dots there. Isn't that just a really ugly power rule with decimals everywhere? So you're probably going to have to just get your calculator and start adding ones. Are we good? Right, so the last couple of Hooke's law questions are 8 and 9. In this case, the information that you're given is up here. And this information is also going to get us K, but it's a different kind of information. The first time they told us the force. In this question, they're telling us the work. But nonetheless, we still are going to be able to find K. It's just going to be a lot harder. Now, it takes 20 joules of work to stretch a spring from its natural length of 20 centimeters to a length of 35 centimeters. Now, I know what the work formula is. It's the integral of 0.2 to 0.35. That's basically A to B of kx dx. Are you happy with the integral formula and where these two numbers are coming from based on the 20 and the 35 centimeters? We're good so far. Now, I know that this number is 20 because they just told me that the work was 20. And I need to find what this integral is. And you might say, well, you can't get it. It's got a K there. Well, you can get it. It just means your answer is going to have K's in it. So here's a little puzzle for you. What do you get when you integrate, right, the antiderivative of K times X? K times X, antiderivative.
K divided by 2 times X squared.
Okay, and you're quite right. I'm just going to call it a half K, but what you said is exactly correct. So far, so good. What do you think I'm going to do next? I've written this down. What's my next line of working going to look like?
You would just plug in the limits into X. So then you'd have the 0.35 squared and the minus 0.2 squared.
That seem reasonable? Now, I could do it as is, but I'm going to do something that I think helps me. I don't know if it'll help you. Sometimes you just do things because in your brain, it's easier to deal with. Can I just pull out the half K as a common factor just to make life a little bit easier number-wise? That's the only reason I'm doing it. So I go to my calculator and I know I'm going to get some ugly answers. 0.35 squared, take away 0.2 squared, leaves me with 0.0825. Okay, we're there. What I would do, although there's more than one way to do this, couldn't I combine the half in this and get K times 0.04125? Are you happy about a half of this gives me that? Okay, we're dead close to getting K, aren't we? I know it took a while, a lot more than the last time, but how will we get K?
Divide each side by that value of 0.04125.
And on the calculator then, 20 divided by 0.04125 comes out to be 470.59 to 2 decimal places. So I now have K. It's 470.59x. Not very pretty answer, would you agree? But if you've ever done engineering or any of the physics classes, do you ever get 4 pi? Don't you just get horrible answers, decimals everywhere? That's just what real life is like. So I guess I shouldn't be too surprised. Now, all we've done right now is question A. Part B, how much work is done in stretching it from 40 to 50 centimeters? Now be very careful about that.
Wait, can I pause you for just a second? Because I think it's gonna mess it up. I think you missed a 1 on your calculator.
I did?
I think it's supposed to be 484.85 if we round it. Because you
I
put.
did.
Yeah. That could
you.
have messed us up on part B.
Okay, I didn't type that into my calculator. I can see in front of me. So can you pretend we fixed it? And so the new correct number is 400 and what?
484.85 when you round it.
Okay, so I just, well, as you can see, I forgot my 1. Good. Now, back to this fella now. Part B. This bit. The work done is the integral from the start number to the finish number of 484.85x dx, right? You might think that it's going to be from 40 to 50, but you know that's wrong, right? Because shouldn't it be decimals and it should be meters? What is less obvious that that isn't even going to be the numbers that I'm going to use. Now I'm going to put them in. It's going to be 0.3 to, let me check that. Sorry, 0.2 to 0.3. Now, since this is the last kind of questions in Hooke's Law, you've got to expect, you know, sneaky things happening. Why on earth did 40 to 50 centimeters not become 0.4 and 0.5, but became 0.2 and 0.3? It's there in front of you, and when I tell you, hopefully you'll say, oh, okay. But see if you can figure out before I tell you, what happened to change the 40 and the 50 to 20 and 30?
20.
Yeah. Now, do you notice in this question, they didn't say stretching it from its natural length, or how would they phrase it? 40 centimeters beyond its natural length to 50 centimeters beyond its natural length. Do you notice they never had that phrase beyond its natural length? And because they didn't have that phrase, that's a raw 40. So 20 to 40 gives you this guy, and that gives you the other guy. Does that make sense now? Now I'm dotting this because would you agree that's just one really, really ugly power rule. Now question C. How far beyond its natural length will a force of 51 newtons? Well, we know that the force function, so we're back to this guy, is that. And we know that this fella is 51 newtons. And we know that K is 484.85. So, oh, wasn't this relatively simple? The question was, how far beyond its natural length? Isn't that just another way of saying what is X when the force is 51, right? Well, when the force is 51, what is X? Divide. And let's see what that looks like. Hopefully I'll put in all the digits. It's going to be a 51 divided by 484.85. And I am looking at approximately 0. To 2 decimal places, 0.11. So that would be 11 centimeters. So what Hooke's law does is essentially is a niche market. Doesn't it tell us what you can do with springs, right? What work is done in stretching it, and questions involving how much force is required to stretch it to a certain distance as well. So you can do force questions and you can do work questions. That's kind of the end of the Hooke's law and springs. Any questions before we move on to pulling things up buildings? Are we good? Right. Get all this out of the way. It's still in the same section, but it's totally unconnected. So don't think of Hooke's law. It's got nothing to do with what we're about to do. I want you to imagine that we have a building. And on this building, there's a person. And this person has a rope that goes all the way down, in this case, let's say at the bottom of the building. And this building is 80 feet tall. And this rope weighs 0.3 pounds per foot. We are going to calculate how much work is done in pulling this 80-foot rope up to the top. So you can imagine a little guy at the top doing this, you know, like the sailors do in the movies, right? Now you might think, oh, that's dead easy. If the rope weighs 0.3 of a pound and it's 80 feet, then the total weight of the rope is just 80 feet times this guy. It's 24 pounds, right? And so I guess that's the answer you're wanting. Well, let's think about this. If you start pulling that rope, aren't you pulling 24 pounds worth of rope at the start? But suppose you get to halfway. Suppose you get to about here. And let's call this distance here X. Would you agree that there's less rope by the time you get to here? In fact, if you think about, if you were that person, wouldn't the beginning of that job be really hard work? Because there's a lot of rope and it's dead heavy. But when you get to halfway, isn't there half as much rope and it's half as heavy and it's a lot less work? And in the last foot, isn't there almost no work at all because there's like almost nothing left to worry about, right? Can you see in this question then the force function, right? The force that you need to pull the rope up the next little bit, doesn't it change depending on how far off the top of the building you're going to be? So we know how to get the work done. The work done is the integral from the start to the finish of the force function. So what we need to do here is figure out how to find the force function. Now, when you're talking about pounds and feet and so on, the force function is in fact just the weight of the rope. And it's the weight of the rope at position X. Okay. If you imagine this is X feet of rope, right? Because you're X units off the top, right? X feet of rope. How much does that piece of rope weigh? Right, if there were 10 feet of rope, how much would it weigh? If there were 12 feet of rope, how much would it weigh? If there was X feet of rope, how much would it weigh?
0.3x.
Does that make sense? 0.3 a foot, x feet, 0.3x. Oh, that force function was dead easy. Right? There's just nothing 0.3 times x. So if we want to find the work done, won't it be from 0 to 80? 0 to 80, right? 0 to 80 of the force function. And I don't have enough room, so I'm going to rewrite it down here. So that's going to be 0.3 divided by 2x squared, evaluated at 0 and evaluated at 80. So that's going to be 0.3 over 2 times 80 squared, take away a whole load of nothings. I'm not even going to try and make that look pretty. I'm not really interested in style points, because it's really just numbers that I need to calculate. And the answer I get is 960, take away nothing, and the units are in this case foot-pounds. Now, if you didn't have calculus, can you imagine how difficult that question would be? How much work is done in pulling a rope up 80 feet? But you see how relatively straightforward it is once we understand that we can use calculus, in this case integration, to calculate the work done. All you need to do is find f of x, the force function, for whatever the story is. Right, it used to be springs, this isn't springs, but it's still a force function, right? That's what you need to get. Now I'm going to ask a question and then we're going to prove it. And I'm going to do it kind of visually. You can tell I'm no good at art. If you pull the rope up to the top, it's 960 foot-pounds, right? We've calculated that. How much work is done in pulling it to halfway, basically, right? Halfway is 40 feet. And how much work is done in that half? Right? So here's the question. Do you think it's going to be the same amount of work to do the first half as the second, or do you think they're going to be different? Alec, you're nodding as agreement on different. What do you think is going to be the harder, pulling it up the first half or pulling it up the second half?
Only up the first half,
And pretty obvious reason would be why. You're right.
because there's more weight to it.
Right. Isn't there more rope in the
Yeah.
first half? Right. More weight, as you say. Does that make sense? Now, the question I guess we need to say is, well, okay, then how much? Well, let's show you. All the hard work is done. Right. If, let's do this guy. We need a start and a finish number. Now, I know this might seem back to front, but isn't x equals 0 to x equals 40? Now, you might say, wait a minute, that looks back to front, but remember how we measured x? Isn't x the distance from the top? So won't x equals 0 mean you've finished, right? The rope's up there. And won't x equals 40 be that one? So this one is, what we call that, the top half. Right. So what about this one here, right? What will be the start and finish limit on this one when you're pulling it for the first half?
80.
Well, definitely 80, do you think? Uh-huh. And what other number?
40?
Yes. Does that make sense? 0 to 40, 40 to 80, right? Right, halfway, right, 0 to 40, 40 to 80. Right, now if we put in the number crunching, which is basically that guy evaluated at 40 and evaluated at 80, and for this one, it's that guy evaluated at 0 and at 40. I'm going to do this one first because it looks easier. 0.3 over 2 times 40 squared, take away a whole load of nothings. 0.3 divided by 2 times 40 squared. And the answer I get is 240 foot-pounds. I don't need to do this calculation. Right. How much is that one? I mean, you could do the
960.
calculation.
720,
720. Correct. What did you do?
just subtracted 240 from 960.
Would you agree these two have to add up to the total work? Do you notice that this guy here is 3 times as big as that guy? Did you notice that? This fella is 3 times as big as that one. Right. 3 240s get you 720, right? Now, is that just a coincidence? No. If I made this weight, I don't know, much heavier, maybe it's a chain, right? And it was £5 a foot, right? These numbers would definitely change, but what wouldn't change is that this would be 3 times that. And you might think, well, does it change if you make the building taller? Well, if I made the building 200 feet tall, these two numbers would still be in the ratio of 3 to 1. So if you pull a chain or a rope, just that, nothing else, a chain or a rope, and you pull it up a building, and you do it in 2 jobs, the first half and the second half. The first half is the heaviest load. It'll take you 3 times as much work as the other one. So we've actually discovered something that might not have been intuitive. Okay, now I'm going to make life even more awkward. We're going to have a cliff this time. And on this cliff, there is a sea. And my little guy's at the top. If you can find my red one. Where's my red one? My little guy is at the top. And there's a poor little guy drowning. And he throws a rope to him. And the rope in this story is going to be 0.5 pounds a foot. And the man, this green guy here, he weighs 150 pounds. And the cliff is going to be 100 feet. And our story is how much work is done in saving that guy's life, right? Pulling him up the cliff with that rope. Now, the way you try and set these guys up is right at the top, pretend that you randomly pick a position which is X feet off the top of the cliff. Now, at that point there, won't you have some rope and a guy? And the force function is the weight of the rope plus the person at position X. Now, I know that the rope weighs 0.5 a pound a foot. So if you're X feet off the top, Are you comfortable with the 0.5x, just like we did the last time? What about the weight of the person? This particular person happens to be a man. What about the weight of the man?
Just add a 150 on the end of it always.
Would you agree that that man is probably not going to be any different at the bottom of the cliff as he would be at the top of the cliff, right? So do you see in this case, the force function is just being adapted a little bit, right? Now, the question was, how much work is done in getting that guy to the top of the cliff? So it's going to be the integral from A to B of our force function, dx. Okay, what number is A and B in this story?
Is it 0 and 100?
We're pulling them all the way to top. If I only wanted to know how much work to pull them halfway up, wouldn't we go, what, 0 to 50 or 50 to 100, depending on how you'd orientate it? Actually, halfway up would be 50 to 100, because we're counting in a weird direction, aren't we? Counting downwards. So the lower you are, the bigger the number. Now, once you've got this set up, it really isn't a problem. It's just, you know, power rule. Well, add 1 to power divide by the new power gets you that. Stick in an x for that guy. Do it at 0. Do it at 100. 0.25 times 100 squared plus 150 times 100. And take away a whole load of nothings. And then I'll just go calculate and hope I didn't turn in too silly. 0.25 times 100 squared plus 150 times 100. I get a little bit distracted because I kind of knew the answer is going to be huge. The work done would be 17,500 foot-pounds. A lot of these questions tend to have huge numbers, right? Just the units, I guess, makes them that way. Are we good so far? Time for one more. Let's have a hole in the ground. Mine shaft. And in this mine shaft, you've got a cage. The cage weighs 100 pounds. In this cage, there's some coal. The coal weighs 50 pounds. This mine shaft is 1,000 feet deep. So here's the surface here. And the cable is £4 per foot. So that's the background of the story. They're pulling up basically a cage full of coal. And it's got a big cable attached to it. Actually, what would happen in real life is there used to be a big drum here. And there's still a coal mine in Scotland that's a museum. You can actually go and see them. So it's basically just a big wheel and the thing went round. Surprising the number of people who were killed in coal mines when these things broke way back in the bad days. Right, so I need a force function. So I'm going to try and imagine that we're X feet off the top, right? Just like we do in the other stories. Someone tell me the force function, which is basically the weight of everything at that position, X feet off the top.
Is it 4x plus 150?
And you are correct. It is 4x plus 150. You want to tell me where the pieces came from?
The 4 represents the cable at position X, and the 100 represents the cage, and the core represents the 50.
Right, so do you notice things that don't change are numbers? Things that do change have an X in them. In this case, the only thing that seems to be changing is the weight of the rope that you're pulling. Does that make sense? So there's a kind of way to tackle these pulling things up buildings, or in this case, pulling things out of a hole. But isn't that just the same math as if it was a building, right? Now, you want to find the work done. I'm not going to finish this because we're running short of time. But wouldn't it be from 0 to 100 to get it to the surface? The guy that we would be using would be this thing. And can we say a ... on that, and you'd be good to go. And don't be surprised when you get answers like 90,000 or 125,000 or some really ugly decimal sometimes. That's just what happens.